Okay, so otherwise I'll be moving on to the next lecture that also contains a few hands-ons for you to do afterwards. And the topic of this lecture is a StarPU runtime system, and the objectives are to learn the very basics of StarPU. So as I mentioned earlier, the StarPU is much more involved, and that's why this lecture is going to be quite long, even though we are learning to do only the very basics of the task-based parallelism. And the overall topics we're covering is that what are the benefits and downsides of using StarPU, how to use StarPU, like how to get it to started and shut down, and then how to create the tasks and using so-called codelets, and then how to pass static arguments between the tasks. And during the second lecture, I will be actually discussing how you can pass so-called data handles between the tasks, from which the StarPU runtime system will then go and generate the dependence between the tasks. So what you can do based on the first lecture is that you can just have tasks that do not have any dependence between them, in the same manner we had during the first OpenMP task lecture, where we didn't yet introduce the depend clause. So as I mentioned, StarPU, which they call it a unified runtime system for heterogeneous multi-core environments. It is a programming AI for shared memory and distributed memory programming on C and C++ languages. You can use it. They have some form of experimental feature that allows you to use StarPU through OpenMP task pragmas. But last time I checked, this support seems to be very experimental and works only with certain compilers. And that's why I won't be talking about it. But at least theoretically, it should be possible to replace the compiler's own task runtime system with the StarPU. There is also limited support for Fortran 2008 and newer, but that is the support seems to be somewhat limited, and that's why I won't be discussing it that much. And then, of course, StarPU supports the GPUs. But it is again a bit more involved than what you can do with the OpenMP or OpenACC. You will end up, most cases, writing a CUDA code to implement the task implementations for the GPU. So first, benefits and downsides. The first benefit of StarPU is that the API is very rich and it's at least partly modular. For example, what things can do is that you can go and customize how the tasks are being scheduled. So you don't have to rely on the built-in scheduler in like the way you can instead implement your own. So you can write it from scratch, or you can do it in use modular design where you use given modules to construct a hierarchical scheduler for yourself. And then you can, of course, write your own modules on top of that. So if you are more interested in experimenting with the scheduling, then StarPU could be a very nice tool for you. Then StarPU uses performance models to predict which resource would be the best option for a given task. So you don't, at least in theory, you don't have to think, should this task run on a CPU or for GPU? The runtime system should be able to do it automatically for you, but there are a couple of caveats attached to that. And then, of course, all these decisions are done dynamically. And then for distributed memory, all the MPI communications are done implicitly. So you don't have to do send or receive or broadcast or anything like that. You just insert the tasks and tell where the data is located. And StarPU will figure out the necessary communication pattern from that data. And then, of course, we have a couple of downsides for when compared to OpenMP tasks. The first one is that the API is very complex and requires more involvement. So just for random experimentation, StarPU is not the right tool. And then when it comes to performance models, these models are only as good as the calibration data that you have for them. So you can pretty easily end up issues with the overfitting. So the models end up with doing wrong predictions, and then you don't really benefit from the GPUs, because the StarPU is either incorrectly thinking that the GPU is way faster than it actually is, or it's thinking that the CPU is actually faster in some instances. And then, of course, the biggest downside is that the OpenMP is a well-established standards, whereas StarPU is not. So StarPU has existed, I remember the earliest paper was 2000, 2009 maybe, or 2011. So it has been there for a while, but it's a research project run by INRIA in France, whereas OpenMP has a backing from several vendors, so hardware vendors, which is always a good sign when you know that there is a support for the tool you are using. Then how do we actually use StarPU? There are pretty much three ways of doing it. The first one are C extensions. So is this a pragmas that you can use in a compiler, but this does not work with all compilers, and that's why I won't be discussing it today. The second approach is just go all the way to the lowest levels of the library and use the API, and it's pretty much a traditional C library. So you go and include a header file, and then you call these low-level functions to talk with the runtime system, and then you will go and link the library with it. So it is a much more involved compared to a pragmas. And then the approach we are using today is that we are using this low-level API, but on top of that, we are using a set of helper functions that make several things, such as inserting a task, much easier for us. And how do you initialize and start StarPU? Since it's the C library, we first have to go and include the correct header file. And most of the functionality you will need today is in the StarPU.h header file. Then somewhere in your code, you have to call StarPU init, and you can give it this configuration struct where you can change the configuration of StarPU. And somewhere else in the code, once you are finished with everything, you have to call StarPU shutdown to shut down StarPU. And then there is this warning that before you go and shut it down, you should either unregister all the data handles, which is something I will discuss during the second lecture, or you should call StopViewTask wait for all to make sure that all the tasks has been executed before you shut down on a StarPU. Depending on a version of StarPU, at least with the older versions, you could actually shut down StarPU before you have executed all the tasks. And then, of course, the results you computed are very ill defined because some tasks get executed and some don't. So this is a quite common mistake to do, that you forgot to wait for all the tasks to finish before you shut down your shut down the runtime system. And let's go and look at the Hello World program, and you can already see what I meant when I said that StarPU is much more involved. So what we have here, we are including the StarPU header file, and then in the main routine, we are going to start the StarPU. And then we are going to wait for all the tasks to finish. And then we are going to shut down StarPU. And between them, we are calling this one function called StarPUTask insert. So we're inserting a task to StarPU, and we are using it by passing it to a pointer to a C struct that is defined here. And the only thing you can find inside the C structs at the moment is just the pointer to a function up here. And what this function is doing, it is just calling printf to print the hello world. So this is quite a lot more code compared to the previous OpenMP example, where it just added a couple of pragmas, and then you were already doing stuff in the task-based manner, whereas here you have to start the runtime system, shut it down, and create these codelets and all sort of things. In order to compile stuff in a Kebnekaise, you have to load a certain modules. So first thing I have here is that I'm just purging what was there before, and then I'm loading a StarPU. So you have to have certain compiler loaded, and also in this case you need the CUDA and OpenMPI, and then StarPU version 1.3.7. And then you compile with the GCC as before, and then you just specify that you want to load the StarPU, you want to link the StarPU library with your binary. And if you're running this this example Hello World program on a machine that's a GPU, then you will get this warning here. And this is here just to tell you that that the runtime system has detected the GPU, and it has noticed that the default scheduler it is using, it is not smart enough to schedule stuff to the GPUs in the correct way. So you will get this warning just telling you that, by the way, if you are expecting this now to use GPUs, that is not going to happen very well because we haven't selected a current scheduler. But for this course, it doesn't really matter, but I'm just including it here in case people run this thing on their own machine or the GPU notion Kebnekaise and can get this somewhat cryptic error message out of it. And this is the first challenge I'm giving you. I would like you to go modify the Hello World program for StarPU and make it so that instead of just inserting one task, you will insert 8 tasks. And even though this example is quite much more complex than the MPI example, I think most people should be able to figure out where the tasks are inserted and what you have to do to insert 8 tasks instead of 1 task. So then actually going into talking about codelets and tasks. So when StarPU is set up, it will create a set of worker threads. And these worker threads are the ones that are going to be doing all the computations. So this is in contrast to OpenMP, where you have the threads active when you're in a parallel region. With the StarPU, you start all the threads when you initialize StarPU, and you kill all the threads once you call the StarPU shutdown. Each CPU core is going to get, on the default configuration, each CPU is going to get its own thread. And if there's a GPU in the machine, then it will allocate one core to manage the GPU to launch the CUDA kernels and that kind of stuff. And it uses a similar sort of approach where the threads will just wait until the tasks become ready, and then they will start executing them. In order for us to have some sort of tasks in the program, we first have to define the task types that we have. So we have to define that there is task type A, task type B, and task type C. And then we have kind of several instances of the task type A running and several instances task type B running. And the task type is defined inside the StarPU codelet. And a codelet is basically a C struct that has quite a lot of fields here. You don't have to fill all of these things. You only have to fill the ones that are necessary. And in our case, the interesting ones are this array called CPU funcs, an array called CUDA funcs, and OpenCL funcs. And what you can do with these things is that you can define multiple implementations for your codelet. So the CPU implementations go in the array called CPU funcs, CUDA implementations go to array called CUDA funcs, and if you have OpenCL enabled, then the OpenCL implementations go to the OpenCL funcs. And in our early example, we know that we have one implementation for the CPU, so we are adding it into the CPU funcs array to tell StarPU that this codelet has one implementation for CPU. And again, you can have multiple implementations, and all the implementations must have this type of prototype. So they take 2 arguments. First one is to a pointer to a void pointer, and second one is just a void pointer. And this is exactly what sort of prototype we have. We haven't been using any of these arguments here yet, but I'll be returning back to this, what these 2 arguments are during the second half of this lecture and the second lecture. And then we come to the second challenge. So I want you to modify the Hello World program as follows. I want you to create a second implementation called Hi CPU World that instead of printing Hello World, it is going to print Hi. And then I want you to add this implementation to the codelet and then see what happens. And then we are going to investigate the part of the code where we are actually inserting the task. So we have this StarPUTask insert function that is going to accept a pointer to the struct. So of course, when we are inserting a task, we must tell StarPU what type of task we want to insert. And that happens by passing to a pointer to the codelet that defines the task. And this function accepts an arbitrary number of arguments, but the last argument must always be 0, and the 0 in the end shown here just tells this function that this is the end of the argument list. And when we actually want to have a task running, then one way of doing it is that we can create a struct called StarPUTask to tell us that what are the features of this particular instance of this task type running. And of course, the key thing here is that the task struct must include a pointer to the codelet that tells StarPU what type of task this is. In most of these fields, I have actually left most of them out. You don't have to care what they are. Many of them are actually related to the underlying, to the way StarPU is actually implemented, so you shouldn't go and touch them yourself. But if you want to really go and customize how the task is supposed to behave, you can go and look into the StopView handbook and see what all these fields mean. So in another example, you showed that we had very simple situation where we just called the StopViewTask insert and then gave it to a pointer to the codelet to define the task. But if you want to do things manually, then you can just go and call StopViewTask create, and this is going to return you a task struct that has been initialized correctly to be an empty task. And then you set up the codelet field to point the code to the codelet that defines the task implementation. And then you can call StopViewTask submit to submit the task to be executed by StarPU. So basically, by using this StopViewTask insert, you are avoiding all the extra hassle. That particular helper routine does all these things for you automatically. And in this instance, it doesn't look that complex, but we are not actually passing any arguments to these tasks. And if you would go and pass the arguments manually, then things get really complex and require many dozens of lines of code. Whereas if you use the helper function, as you will see later, you will end up just writing a few lines of code for each task you are inserting. So let us now return back to these task implementations where that always had this kind of prototype, and it has these two arguments that are passed to every single task implementation. So the first argument defines an array of data handles. And this is something I will discuss in the second lecture. Right now, I'm more interested in the second argument that defines a list of task arguments. And these task arguments are meant to be static, so they do not generate any data dependencies. They are just very handy if you just want to pass on static variables to tasks. So let's look at the simplest possible example. I have modified this hello world example slightly. So inside the task implementation, I'm taking this second argument, CLArgs, and then I'm extracting from this argument a pointer to a C string, and then I'm just printing the content of the string. So all these static arguments are packed inside this abstract object called CLArgs, and you can then use the StarPU codelet unpackargs to go and unpack the values from the packed object. And in the main routine, I'm just have a C string that says hello world, and then I've done a minor modification to the StarPU task insert routine where I'm saying StarPU value, then I give a pointer to this C string, and then I'm just telling it how big this string is. So I'm giving that, and all this information is now, what happens here is that it is going to take this information here, pack it inside the task, the StarPU task struct, and then pass on it to the task implementation, and then it's going to go and unpack the string from this packed object. And again, the output from the code is the same, because what happens here is that it will basically just take the string here, it will copy the contents of the string to this packed object, and then I'm gonna unload the content of the string inside the task implementation itself. This is just explaining things in more detail. So every time there is a StarPU value, it indicates that there is going to be a static argument passed to the task, and it must always be followed by two additional arguments. The first one is the pointer to the task argument, and the second one is the size of the task argument. So when you submit the task, it is going to take whatever the argument is and use the size to copy it entirely into this hidden underlying object that stores the task arguments. And it is all unpacked with the StarPU codelet unpackargs function that accepts a pointer to the second argument passed on to the task implementation, and then it has an arbitrary number of pointers to the variables where you actually can unload these arguments. And previous example, we had just one argument being passed on, but you can actually pass an arbitrary number of them. And of course, in the main routine where you're inserting them, you just have any type of variables you want. That can be of different types. In this case, we have a total of X arguments here. And for each argument, we will have StarPU value indicating that we are passing an argument. Then we will pass a pointer to the argument, and then we are given the size of the arguments for all of them. And in the task implementation, we will go and unpack them in the same order. So we again have to have a place to store the value of the argument. And then we will call StarPU let unpack args, and we will pass on the second argument given the task implementation. And then in the same order as here, we will give pointers to the variables where we are going to actually unload the arguments. There is a slight typo here. This is a pointer here as it should be, but these should also be pointers to these variables up here. Then I have a challenge for you. So I would like to modify the following program so that you will go and pass two integer arguments to this hello world task implementation here, and then print out their sum. So very simple thing. And right now, this is going to finish the first lecture on StarPU. You can see that it was somewhat long due to the fact that StarPU is much more involved, but the hands-ons themselves should not be overly complex, I think. So for now, I believe that I'm going to be waiting until, let's say, 10:25. I will come back and then check the situation, how people are doing, and then make a decision based on that, if I should move on to the second lecture or not.